Hey, welcome. Today, we're going to pull back the curtain on two huge ideas that are secretly running the show, from the coffee brewing in your kitchen to, well, the entire universe. Yep, we're finally going to make sense of enthalpy and entropy. So, let's start with a little puzzle. What on earth could a running refrigerator and a steaming cup of tea possibly have in common? It sounds like the setup to a bad joke, right? But the answer actually unlocks some of the most fundamental rules of energy in the cosmos.
First up, let's tackle enthalpy. The easiest way to think about it is just as the total amount of heat energy that's packed inside of something.
Okay, so here's the official textbook definition. You see words like internal energy, pressure, volume, and yeah, it sounds super complicated. But really, all those technical terms are just a fancy way of saying we're adding up every last little bit of heat in a system.
Think about it this way. A system can suck in heat, kind of like a pot of water getting warmer on the stove. And it can also give off heat, like that hot cup of coffee cooling down on your desk. Enthalpy is just the grand total, all the heat something is holding on to at any given moment.
So the big takeaway here is that enthalpy is all about quantity. How much? It's a number, something you can measure. But how that heat is arranged and what it's probably going to do next, well, that brings us to our second big idea.
And now for entropy. This one's a little trickier. If enthalpies is the what, the amount of heat, then entropy is the why. It's the hidden rule that explains which way things are heading. And spoiler alert, that direction is almost always towards a bigger mess.
So the formal definition calls it a measure of molecular disorder or randomness. Basically, it's a way to put a number on chaos at a microscopic level. It might sound abstract, but you see the results of it absolutely everywhere.
Just look at this. On the left, we've got a low entropy state. Everything is neat, tidy, and in its place. It's predictable. But then look at the right. That's high entropy. It's the same exact molecules, but now they're just a chaotic, random jumble. There is no predictable pattern there at all.
And this right here, this is the crucial law of entropy. Nature always favors disorder. Think about it for a second. A sandcastle will always crumble back into sand. A hot coffee will always cool down to room temperature. It takes a ton of energy to create order, but things falling apart into a mess, that happens all by itself.
Okay, so we've got enthalpy, the total heat, and entropy, the tendency to get messy. Now let's bring these two powerful ideas together and get back to our original puzzle, the refrigerator. So let's just recap real quick to lock it in. We're looking through two lenses: enthalpy, which measures the total heat in a system, and entropy, which measures the level of disorder in that same system. You know, your refrigerator is basically an entropy-fighting machine. Seriously, it's waging a constant war against nature's natural desire for things to get messy. It uses energy, electricity from the wall, to actively pump heat out, creating a cold, ordered, low-entropy bubble where your food can stay fresh. Okay, let's look at the trade-off here. Inside the fridge, we get exactly what we want. Low enthalpy because it's cold, and low entropy because our food stays organized and fresh. But that order doesn't come from nowhere. The fridge has to dump all that heat and disorder somewhere, and that somewhere is your kitchen. That warm air you feel coming from the back, that's it. It creates a tiny pocket of order inside by creating an even bigger amount of disorder outside. So on balance, the total messiness of the universe still goes up.
So, we've seen how these laws run our kitchens, but they also run the entire cosmos. If the universe itself is one giant closed system and its entropy is always increasing, if everything is constantly moving from order to disorder, what is the ultimate fate of everything? Now that is a question to think about.